So today we are continuing our conversation using the NRTL model for calculating vapor-liquid equilibrium problems. And in the previous video, we calculated the bubble point and dew point components. Today we'll be doing something a little bit different, which is called a flash calculation, where we are going to set our composition, our temperature, and our pressure. And based off of that, we are going to calculate the liquid composition and the vapor composition. So far what we have is what we had in the last video, with the exception of the temperature, which we'll be calculating using a different method. We have a isopropanol water system in an equal molar ratio. We have atmospheric pressure, and we have all of our calculations needed to estimate our temperature, which is going to be halfway between the dew point and the bubble point to ensure that we have a vapor-liquid equilibrium. So the first step that we're going to do, I'm going to define a new function. We're going to call this flash NRTL. And we're going to call this the PT flash. And we're going to have inputs of the Z, the composition, the pressure, and the temperature. Now, when we had done a flash calculation using Raoult's law, we used something called a Rachford-Rice calculation, where we calculated a phi variable that would help us calculate the vapor composition based off of the K and the phi. And we can do something quite similar, actually, for our flash calculation using the NRTL model, except in this case, instead of having, I can write this out. So we defined K as our ratio between our Y and our X, our vapor composition and our liquid composition. If we write out our modified Raoult's law, which looks something like this, X P sat, subscript I is here, is equal to Yi total pressure. If we wanted to get our K, we could divide our X over, so we have gamma I Pi saturated equals Kp. So then what ends up happening is that our K is equal to gamma Pi saturated over our total pressure. So that will be our first step in coding out this function. So let me go ahead. So we have a gamma, so we're going to use our library to get our gamma, and this is a function of our composition and our temperature, our liquid composition and our temperature. And you'll see the issue with that in a moment, but let's just go ahead and code the rest of this out. This is followed by our saturated vapor pressure, U.Pvap, at our given temperature, and this is all over our total pressure. Now, the issues here, we have an input of temperature, and that's fine, but we don't have our liquid composition. And so what will end up happening is that we'll need to make an initial guess for this liquid composition before we even do our flash calculation. So that is something that we need to iron out before we move on to the next step. So the first thing that I want to do here is I think I could probably do this outside of the function. You don't know. I'll do it inside. First, what I'll do is I'll unpack our results from our bubble temperature and our dew temperature. So we have a bubble T, NRTL, and we have inputs of our feed composition and our pressure. And remember that this bubble T returns us our temperature and our vapor compositions. So we could say something like, we'll unpack this into our bubble T result and our bubble Y result. So that will give us our temperature and our Y's independently. And what I'll do is I'll do the same thing for our dew point. So change all these to dew. So dew temperature. This will be a dew liquid composition, because remember the dew point is where we have our first drop of liquid in our system. So we're going to have dew liquid compositions. And this comes from our dew calculation. And the last thing that I'll actually do is we want to take the average of our bubble temperature and our dew temperature to give us a temperature that we want to use for our see, now I think in this case it makes more sense to do this outside of the function, because we want to input our temperature. Oh no. There we go. I think it makes more sense to do it this way because we want to input our temperature into our function. And then I'll say something here like the flash temperature. So flash T is going to be equal to the average of our bubble T and our dew T. So that will be our bubble T result plus our dew T result and divide by 2. And that'll check out. Now, remember that our initial problem is the fact that we don't have an initial liquid composition gas yet. But we can actually obtain one if we understand how our compositions and our bubble and dew temperatures are related. And so, here's what for illustration purposes, I'll draw out a graph. So, we have, so let's say over here, down here, we have our bubble temperature. Up here, we'll have a dew temperature. And we have a point here, and this point correlates to our feed composition, our Z, which you remember is equimolar. And we'll have some composition up here, and this will be our liquid composition. So X1, X2. This will be our liquid composition up here that is provided by our dew temperature. And so these 2 points, we'll assume it has some sort of linear, we'll have some sort of linear relationship here. And what we'll end up doing is we'll choose some temperature right here in the middle that correlates with some point on this line, which by extension correlates to some initial liquid composition guess. So this is the approach we're going to take to get this initial X value guess that we have, and we'll use that to calculate our K and continue on with our Ratchford-Rice calculation. So let's start approaching this. So I'm going to do this now inside of our function. All right. So I'm going to call this our X naught. This is our initial liquid composition guess. And we'll say, so we'll follow y equals mx plus b. It's a linear interpolation. So first, we need to find our slope. So what's our rise over run? Well, we have some z composition that we're starting at, and we're going to subtract from it our dew x res. That one right there. And this is going to be over our temperature difference that's on the x-axis. So that's going to be, we'll start at our T and minus our dew T res. All right. And now we'll have to multiply this by our x, so I'll throw that in here, and that's going to be our T minus our do T res, or, oh no, this should be our bubble T here, because our bubble T correlates with our feed composition like we stated earlier, and our x is our do T res, so our difference between our temperature that we want to do our flash calculation for and our temperature that we are given. Gonna change that to x naught because that's what we'll be using that. And then finally we add our starting point, which is our do x res. All right. Now this linear interpolation should give us an initial guess to calculate our k value using this gamma function that we have here. So from now, we continue on to using this k value in the Rachford-Rice to perform our flash calculation. So what I have pulled up here is the Rachford-Rice solver that we had coded previously in a previous video. And what I want from this is this amount here, this function that'll give us our phi value. And what I'm going to do is I'm going to create a for loop. So for I in range, let's say like 100, something like that. What I'm going to do is I'll have a k value there that is defined by this initial guess that we are making. And what ends up happening is that we want to minimize the amount of error between our x naught guess and the x that is calculated through our Rachford-Rice. So if we look here, we have this function that solves for phi, or solves for an input of phi, and this input comes from solving this root here. So we have our function, our target function, we have an initial guess using the Newton's method, and this phi basically is based off of this optimized function that is available in the SciPy library, and this gives us the value of phi that completes this function equal to 0. And we will be doing this over and over again until, so if np.linalg.norm. This is a method of getting us basically a method of least squares. This is an error matching or an error confining function. Say that x minus x naught is less than some tolerance. So less than, let's say, 10 to the minus 6th, something like that. Then we break out of it, which means we break out of this loop, this for loop that we have. Otherwise, we update our initial guess to equal x. All this should be indented. And then this. So just to go through the logic here, we'll have an initial guess that is based off of our flash temperature here and these calculated values that we have from these previously coded functions. What that'll do is that'll calculate us an initial value of our k, which is to be used in our target function for minimizing our phi. Basically, the sum of our compositions, -1, should equal 0. So we use our root scalar using our Rachford-Rice target function and an initial guess using the Newton's method, which will calculate us a value of our liquid composition. using this calculated phi value, and we keep checking to see that the error between our calculated x and our guessed x, making sure that that error is minimized below a certain tolerance. Otherwise, we set this initial guess equal to this x value here, and we continue on with that loop. So now the last step here is we're going to want to calculate our final y value. So we're just going to use our modified Raoult's law to get that. So we're going to pull, so that'll be x times our gamma, our activity coefficient. And this will also multiply our saturation vapor pressure. All of this is over our pressure. And we'll do a return. And what we want to return out of this is we want to return our vapor mole fraction, our phi. Want to return our liquid composition, and we want to return our vapor composition. So vapor mole fraction, liquid composition, vapor composition. So now if we go in and we give it our function, our inputs, so we have our equimolar composition, we have our atmospheric pressure, and we have our flash temperature, which, if you remember, is the average of our bubble temperature and our dew temperature. If we go ahead and run this program, you see that we get nice values for our phi, x's, and y's. So we have successfully conducted a flash calculation using the NRTL model given a constant pressure and temperature.